So why don't we get started? I'm Dan Freed. I'm director of the Harvard Center of Mathematical Sciences and Applications. We're a center that's devoted in large part to a two-way interaction between mathematics and science. You can find out more about the CMSA at the links in the chat. And today that science is AI. And we're very happy to have the four editors of the First Proof project that will be discussing their project and where they are, their goals, aspirations, and so on. CMSA is proud to, in part, sponsor some of their activities. And so let's begin by introducing or having the four of you introduce yourselves. Go ahead, Nikhil.
Hi, I'm Nikhil Srivastava. I'm a faculty in math at Berkeley and a senior scientist at the Simons Institute. And I'll say more about my math later in the talk.
Okay, Mohammed, you're next on my screen.
I'm Mohammed Abouzaid. I'm a professor of mathematics at Stanford University. I study symplectic topology and mirror symmetry, even though these days most of my time is being spent working on this project.
And for those people who don't know what symplectic topology and mirror symmetry is, do you want to say a few words about that?
Well, yeah, symplectic topology is the study of smooth manifolds equipped with the analog of area forms. So it's some kind of strange cousin of Riemannian geometry, where instead of measuring lengths, you replace that with measuring area. And mirror symmetry is a subject that originated in string theory in the 1980s, and some very unexpected correspondences between numbers produced about integrating of some certain differential forms on varieties, and other things being like counting number of lines, a number of solutions to algebraic equations on other spaces. And it got elaborated into a very theoretically deep connection between symplectic topology and algebraic geometry, which is basically the study of solutions of polynomials.
Great. Lauren?
Hi, I'm Lauren Williams. I'm a professor of math at Harvard. I'm also on the scientific board of CMSA, and my research is in algebra and combinatorics. But a lot of what my research involves is applications to different areas of physics. So I've had some work to do with models of particles from statistical physics, and some of it has had to do with the study of shallow water waves and soliton solutions of the KP equation, and some of it has to do with scattering amplitudes in n=4 super Yang-Mills.
Okay. Rachel?
Rachel Ward. I'm a professor in the math department at UT Austin. My research is in applied math, specifically the analysis of randomized algorithms with applications in digital signal processing and large-scale optimization. I've worked on the analysis of stochastic gradient descent, and my work led me to do some stints in industry, first at Meta, working on stochastic gradient descent, and later at Microsoft Research, working on training open source small language models.
Okay, great, thanks. Let me mention to everybody that's participating, there's a Q&A button, I think, on your Zoom. If you want to contribute questions as we go along, certainly at the end, then you can type them into the Q&A. So let me ask, what's the origin of First Proof? And someone should outline what the goals and just what the First Proof project is, and then I'll ask each of you how you got involved. But first, let's hear about what the First Proof is.
Well, I would say kind of First Proof is an attempt at having an independent assessment of how well AI can do some part of research mathematicians' job, I would say, and not the different way of thinking about it is how much can it assist in that work. Now, we tried very hard to think about something that we could actually measure, that we could say, it does this well. And in the process of doing that, we basically identified something that is fairly natural to imagine, which is to take statements that that require proof and see whether the AI machines can prove them, and then check how correct these proofs are. So that's roughly speaking where what the project is, at least right now.
Okay. Lauren, how did you become involved with this project? Oh, you're muted, I'm afraid.
I got an email from Mohammed and Rachel, and they said just a few words about this project. And Mohammed was passing through Cambridge, and we wound up having a dinner conversation about it. And I guess this was, I don't know, 6, 9 months ago, something like that. And I'd gotten intrigued by the possibilities of AI. I had attended some of the workshops and talks actually that CMSA hosted on AI and machine learning, and I thought this sounds like something I should be learning about and getting involved with.
Did you use AI in your own work before this or since then?
So not before this, but I've started to try to do so with mixed results, I would say. I've asked it to prove lemmas, and sometimes I've been in a situation where the beginning of the proof starts by reiterating all the correct statements, and the proof ends by sort of claiming that everything's neatly tied up with a bow. But sometimes, in some situations when I actually start checking the details, it turns out to actually not be correct. It starts claiming statements that would make the proof easy, but just happen to be wrong. But I've also had positive experiences, and not too long ago, I needed a kind of Coxeter theoretic lemma for a paper that I'm in the process of writing, and my collaborator and I thought this lemma must be true. It sort of looked true, it smelled true, didn't look like it should be so terribly hard to prove. It wasn't in the books or papers. And I thought, okay, this is a good test case for AI. So I gave it to a model and got what I later verified to be a correct proof, maybe an hour later. I've also tried a little bit to use it to sometimes help me fill in details when I'm preparing a lecture on material where I know the outlines of the what's true, but maybe not the details. And sometimes it can be helpful, but sometimes I've run into a situation where it will give me a correct proof of a lemma by saying it's a special case of some sort of powerful theorem, some other source that I then have to look and make sure it's correct. But in some of these cases, when I actually sat down and thought about the lemma, I realized there was a 3-line intuitive proof. So sometimes AI may give a correct solution, but not the solution that you want. So I would say, it can be a powerful tool. It can also be a tremendous time sink if you're not using it right.
Okay. Nikhil, how did you get involved with this project, and what are your own kind of goals with it?
Well, I also got an email from Rachel and Mohammed, who, as far as I know, started this. And I thought it was very interesting because I didn't know what the outcome was going to be. I was very curious. I thought it was a very clean experiment. It was very timely. And I was just like, yeah, either way, this is going to be really interesting. And so I was like, yeah, I'd like to be involved. Yeah, my experience is, I use it regularly, mainly to do like numerical experiments in areas where that's possible. I've tried using it to prove things and had kind of similar experiences to what Lauren said. And I'm interested in learning how to use it more effectively.
So Nikhil, experiment means like basically using coding assistants to like write code for you?
Well, both. So sometimes using coding assistants to write code, but sometimes you just tell like ChatGPT Pro, like just do this experiment. So it will run the code for you and just tell you the results.
I see. Okay, Rachel, you are apparently one of the progenitors of this first proof. So yeah, tell us a little bit how it came about?
Oh, well, a mutual acquaintance, I guess, told me to talk to Mohammed. I was coming back from industry, back to academia full-time in the math department. And on my end, it was quite shocking, the different views towards AI and math in industry versus in academia. This was last year. In industry, I knew that a lot of resources and a lot of people, mathematicians, were dedicating, full time to making AI better at mathematics. And back at UT, it sort of seemed a little bit like people didn't maybe know what was coming, or like the seriousness of what was coming. But when I talked to Mohammed, he got it. He was like, I want to do this benchmark to assess AI capabilities in mathematics. And my contribution was, he was looking for how to fund this. And I said, I don't think we have time. Let's try to do this without funding initially. And so that's how we came up with the design of getting mathematicians together. I thought Nikhil would be helpful with the Simons Institute for possibly being a venue to help the first initial meeting, and sort of get an archive paper out with the project to sort of get things started.
Okay. Mohammed, do you want to add to that?
Well, I mean, from my point of view, I started thinking about this in about November 25, maybe a little bit before then. So my viewpoint, November 24. So my viewpoint is basically that it was becoming clear that the AI companies were starting to think of mathematics as some kind of test bed for the capabilities of their models, and that makes a lot of sense. In maths, the result is either true or false, and that means you can check whether a machine has produced adequate output or not. And it was there was some process where mathematicians were getting involved with AI companies, and it was taking more and more of public discourse. You could hear about it, and it was never clear the level of independence that various people speaking about AI and math had. And my view is that if there had to be a voice that was not, I mean, I would say neutral, but at least something that really represented the point of view of mathematicians. Of course, my point of view initially is that, oh, maybe we would go to the American Mathematical Society or the NSF or somebody like that. But the pace of the AI companies was so fast, and this is somehow the thing that Rachel kind of impressed upon me, that we cannot wait like 6 months for the NSF to make a decision. We really just had to go ahead and decide to kind of try to do it as a community effort. And from then things just, steamrolled and moved very, very quickly.
I see. So being at Stanford, do you think you're more exposed to you said you didn't need to be, or Rachel said you didn't need to be convinced of what's coming to us, whereas in Texas, a little bit further maybe from the epicenter. I mean, how does it affect things being right at Stanford? Do you feel that on campus, a little more the influence?
I think we see it very strongly, for example, in our computer science department. I think in mathematics, it's mostly visible at the level of the graduate students. Of course, I should also kind of place myself back a year ago, but I would say even a year ago, it was mostly visible at the level of the graduate students. They have friends working at the AI companies. Some of them were already thinking about taking internships at these AI companies. And so they talked to each other, and they could see that there was a lot of money being put in developing these systems, and it's going to have some kind of output for our work. I would say at the time, it was not so much anxiety yet. I think now it's more anxiety about it. But at the time, it was more just curiosity and thinking that like, oh, there's this big thing coming, what's going on in these labs. When you're a professor in a math department, you can just close your door and ignore what's happening outside. But if you do decide at Stanford, if you do decide to open your door and talk to people, then indeed it's more visible quite, very quickly. You can start talking to people who have ties to AI companies who can tell you what's happening.
Okay, good. So let's get into a little bit how first proof works. If one of you wants to tell yeah, the initial round you had, just how you structured it, how it happened. Yeah, just the structure of what happened in the first round of problems. Any of you?
Rachel, did you want to take that? I mean,
Sure.
it's
we invited several mathematicians to participate by providing a research level math question that came organically from their own research that they already had worked out a solution to, but had not yet talked about or posted to the archive. So it was just within them or them and their collaborators' heads. And we invited mathematicians trying to represent a breadth of fields within mathematics to share a question for the first batch of first proof. And then we got together around last December 2025, and we, at the time, the best publicly available system, AI system, was probably GPT 5.1 or 5.2 Pro. And so we tested some of the questions as a group to see how the AI system did. And sort of noticed that on some questions, it did better than we expected, just being a few months behind. I mean, it was advancing very quickly, and others not. But so we decided on a final set of 10 questions based on trying not to cherry pick, but trying to find that border at which the border of capabilities of the AI systems, where they were just below or just above the capabilities. And I myself tried, I was coming back from being in industry, and I tried to write a question, but at the time, actually, I couldn't find a good question that the AIs didn't solve. So my own areas that I had been working in seemed to be more difficult to generate questions at that boundary.
I see. Okay, so maybe this is a good time, Nikhil. I think you have a presentation of one question, and we can.
Sure, yeah. So so as Rachel said, there were 10 questions, and they arose naturally in people's work. So most of them were parts of papers, were lemmas, or were steps in something bigger. And I will tell you about my problem, which is a theorem. This is problem number 4. So to introduce this problem, the kind of original context is classical probability. So I'll tell you about a famous theorem in information theory called Stam's inequality. So the basic object here is you have a probability density on R, and let's define its Fisher information to be the L2 norm of the derivative of the log of the density squared. Okay, so if you've never seen this before, you might find this unmotivated. But the important thing about this is that this quantity is minimized for Gaussians, subject to normalizing the variance to be 1. So it's you can view it as some kind of measure of Gaussianity. It's a standard quantity in information theory and statistics. So that's the Fisher information. And then you can ask, well, what happens to the Fisher information when you convolve 2 measures? So for some pedagogical reason, I'm going to define the convolution of 2 measures in terms of the Fourier transform like this. So you have mu and nu, and you can define its convolution. And then, we know that if you keep convolving a measure with itself enough times, subject to some regularity, you have the central limit theorem, and you should get a Gaussian. And you can ask, well, what happens to the Fisher information when you do this convolution? And this is a famous theorem of Stam. Stam proved that the reciprocal Fisher information is superadditive under convolution. So this is called Stam's inequality. So for a pair of densities mu and nu, we have this inequality. And what this shows is that if you then use this to study the central limit theorem, it can be used to show that the entropy increases as you take variance normalized convolutions of a measure. So if you take sums of independent random variables and normalize so the variance stays constant, the entropy increases. So that's a very conceptually satisfying conclusion. Any questions or comments about what Stam's inequality says? Okay. So important for this talk is that the proof of Stam is a very beautiful short proof. It crucially uses the notion of a joint probability space. So you have two independent random variables with these densities. You need to consider some functions defined in the joint probability space, and you need the concept of a conditional expectation to prove this. So, okay, what about problem number 4 in first batch of first proof? So this belongs to a different area, which sometimes is called finite free probability. So the basic objects here are, instead of measures, they're univariate real-rooted polynomials. So let's say you have a polynomial p of degree n with n real roots ai. Then it turns out this is the correct definition of the Fisher information. I won't motivate this or explain why. It was defined by Dima Shlektenko. And this is some kind of Coulomb potential of the roots. It measures, how far the roots, for example, if there's a multiple root, it's infinite. And again, this quantity is minimized for the analog of Gaussians in the setting. It's minimized for Hermite polynomials. If you normalize the variance of the roots to be 1, this Fisher information is minimized for Hermite polynomials. So in this different setting of polynomials, there's a different convolution, which is natural, which goes by many names. So I'm going to call it the Walsh convolution in this talk because it first appeared in work of Walsh in 1922. So the Walsh convolution is defined in terms of a type of Fourier transform. So if I have a polynomial p, univariate polynomial p, I can view it as p hat of the derivative applied to x to the n, and let's call that the Fourier transform. Then the convolution of two polynomials is the one you get by multiplying the Fourier transforms. So this is a very elementary definition of this convolution. It originally appeared in the context of invariant theory, but recently it's with Marcus and Spielman, we realized it's related to random matrix theory in some way, which is how we became interested in this. Any questions about these definitions? Okay. So once you have these, there's a very natural question, which was asked by Dima Shlektenko in 2015, which is the Stam inequality true in this setting of finite free probability? So for a pair of real-rooted polynomials, do you have this Fisher information inequality? If this is true, it shows that the discriminant of the polynomial increases in the analog of the central limit theorem. And it has connections to other areas of math, such as free probability, and it implies various results about how the zero spacing of polynomials changes under applying differential operators. So this is the conjecture, and this is problem 4 of first proof, batch 1, this exact conjecture. And I should say the reason people were interested in this conjecture, apart from these applications and kind of that it's a natural analog, was that there was a mystery behind this, which is, well, in the classical case, you needed this notion of a joint probability space. And people thought that if you want to solve this in the polynomial setting, what is this analog of a joint probability space? There's no actual randomness in this right-hand side of the slide. So what should this object be that plays the role of a probability space? And that was in some sense the motivation for this conjecture. So this is problem 4. Any questions about the statement of problem 4?
So at the time, this was a conjecture. I mean, it wasn't known.
It wasn't known. Well, sorry. So the problems in the first batch were problems that had been privately solved by the authors. So as I explain in the next slide, with my co-authors, we solved this problem. So let me now explain about the human story. So humans.
If I could interrupt, we do have a question from Rita Amadi, which is, was the conjecture open for all P and Q, or had some specific P's and Q's been solved? Yeah.
So for Hermite, it's easy to just check this is true with equality. And as far as I know, it was open. It had been proven in maybe degree 3, but it was open beyond that.
Okay. Thanks.
Okay, so I'll tell you about two solutions to this, a human solution. So 3 humans, so me and my 2 collaborators pictured here, thought about this on and off for about 8 months in 2025, not 2026.
Yes.
Kind of in combination with a lot of other related problems. And in November, we completed a 5-page proof of this. And here are 3 features of the proof I want to highlight. So importantly, the proof is guided by the construction of these conditional expectations that were sought in this different setting. Now, to analyze these conditional expectations, some connection to another area of math was required. Even though this is a problem about univariate polynomials, a key input came from this theory of multivariate hyperbolic polynomials due to Gording, which came up in PDE in the 50s. And this was used to establish some log concavity or negative dependence type properties for these conditional expectations. But once this object was defined and these properties were established, the classical proof just worked. You didn't need a new proof. And so in some sense, this was a satisfying solution to this mystery of, well, what is the joint probability space in this setting? Any questions or comments on the human solution of this problem? Okay, so we thought this would be a nice problem for first proof because it has a short proof, and the proof seems to require drawing attention to an object which hasn't really been considered in this context. And to my surprise, one team solved this problem in first proof batch 1. So we posted on the internet, we gave people 1 week without really specific rules, just guidelines for, like try to autonomously find solutions to these problems and report what you did. And OpenAI gave a submission with the following process. So they queried an internal model with limited human supervision for 1 week. Okay, so what does limited human supervision mean? So this is highlighted because it's meant to refer to a quote in their blog post. So here's what they said about their process. They said, we ran the model with limited human supervision when prompting versions of the model along training because their model was changing during this week. We sometimes suggested retrying strategies that appeared fruitful in earlier attempts. For some attempts, we asked the model to expand or clarify parts of the proof after receiving expert feedback to make reasoning easier. For some problems, we tried the best of few attempts. This was a fast sprint, and the process was not as clean as we would like. So this is a quote from their blog. Okay, there's a question. What was the analog of joint probability in this space? I'll refer you to the archive paper for that. There's a construction of conditional expectations. Yeah. Okay, so this is the process that OpenAI produced, that OpenAI used. And the product of this process was an 8-page proof, which was correct. So the proof was kind of hard to read, and it took people, there was no formal refereeing in the first round. So it took a while for it to be read line by line, but eventually with my co-authors, we checked every line and it is correct. And it's very interesting because it's different from the human proof. And I want to highlight three differences. So one is there's an important step in the proof where it uses something called a polar derivative, which is something that goes back to Laguerre, to turn this problem, which is a problem about zeros of polynomials, into a problem about critical points. And it's not super clear at the beginning why you would do that. But then it executes a bunch of steps, mostly just like identities, using only elementary like 1800s math, like residue theorem, things like that, which eventually yield this result in a way that's kind of magical. In that it wasn't clear what the overarching narrative of this proof is, but the proof works and is very clever, and if you want to call it that. But it kind of has different explanatory power from the human proof in that it doesn't really address this mystery of like, does it give you some object that you can then use as some kind of joint probability space? So both this process and this product are very interesting and different from the human ones. So any questions or comments about these?
So Pavel Eddinghoff has a question. Did the experts have math input during the process?
Right. So they didn't really say. So we know experts were contacted. in some places, like in one blog post, they said we did not provide mathematical input, but then in another place they said the experts corrected errors. And then even in this blog post, it says we suggested retrying strategies that appeared fruitful in earlier attempts. So it kind of depends on what you consider to be mathematical input. So I don't know, I think is the answer.
Did the model in its solution at all connect with the previous, version of that inequality?
You mean the classical stem inequality?
Yeah, exactly. I mean, the human proof did, right?
Right. I don't think so, which is very interesting.
Yeah.
I mean, there are some points of contact between the two proofs, which maybe I can discuss later. But the OpenAI proof, I don't think makes much connection with the classical proof. Interestingly, it really doubles down on this particular identity it derives using the residue theorem, which did appear in our preliminary GPT 5.2 Pro test, something like that. Like it wanted to use the residue theorem to do something. And so we can speculate, but I don't know how it came up with this.
Yes.
So what's the interpretation of this? Well, okay, one thing we can conclude is AI with limited human supervision can solve an interesting problem in 1 week, interesting to me at least. And okay, by now we have other examples. But this raised another mystery, which was discussed in the online discussion, that where did this polar derivative idea come from, and why was it pursued? And we've seen discussions like this around other problems. And we just didn't have enough information to answer this question in the first round because the model, the prompts, the amount of compute, and the expert input were proprietary. So beyond this blog post, we didn't actually know the process. And this kind of leaves us with, well, that's what we want to do in the second round. We want to have as much clarity as possible about the process so we can interpret the results kind of clearly. Any other questions?
There was a question about whether OpenAI knew that we had a solution.
Yes. So in the first round, when we posted the 10 questions, we explicitly stated that we have a solution of at most 5 pages. So everybody knew that there was a short solution to all of these problems.
And moreover, we encrypted our solutions and released the encrypted solutions the same day we posted the problems.
Yeah. That was a fun aspect of it.
Did the models try to decrypt your solutions?
I think they're too smart to try to do that.
There was no evidence that this happened.
Okay.
Anyway, that's all I want to say about problem 4.
Oh, that's fantastic. I think that gives us a great insight into one of the problems, which I think is very helpful for all of us. Patricia Ewald asks, were there other solutions submitted to that particular problem?
Okay, so there were a lot of kind of solutions given by, I would say, amateur mathematicians or mathematicians, which really tried to execute the classical proof by defining some kind of joint probability space, but they were all like totally wrong. Interestingly, Google DeepMind output no answer for this solution. And so there was nothing even close there was nothing that everything else submitted was clearly wrong, except for this thing, which was correct. And then there's another question, does this polar derivative idea exist as a new invention, or is it a combination? It's not a new invention. It goes back to Laguerre. It's sometimes called the Laguerre derivative. It's a device that's used in this area generally, but it's not clear why you would use it for this problem, at least to me, at the outset. Like, you have to, until the end when you see that it works.
Okay, so maybe stepping back from problem number 4, just thinking about the collection of 10 problems. Lauren, do you want to say something about the kinds of areas that those covered and then what the results were of the first batch?
Yeah, so we tried to cover a sort of broad range of fields, all 10 problems came from different areas of math. We had one in symplectic topology, we had one in algebra and combinatorics, we had some more in algebraic geometry, and let's see, so we put out these 10 problems, each of which had come from our own research, and then, basically when we put out these problems, we didn't really say these are the rules by which you must solve them. I mean, we sort of suggested in our paper that the right way to do it was to give an AI model one shot to answer the question. I think we brought up the point that once if you ask an AI model a question and then start going back and forth, and it becomes a conversation between a mathematician and an LLM, it becomes hard to distinguish what's the contribution of the LLM versus the contribution of the mathematician. So we sort of gently suggested what we had in mind, but we didn't sort of make a hard and fast rule. And so, of course, the solutions produced were produced in all manners of ways. And we generally didn't have transparency about the process by which they were produced. But that being said, if you sort of look at the best solutions for each problem submitted by all the different organizations and individuals, somewhere between 6 and 8 problems were solved. And I should say also, we didn't do any formal grading of these problems. We didn't have the time and manpower to do so. As many people know, it's quite time consuming to check a math proof, let alone an AI generated math proof. But what we did do was have a zulip in which people were invited to post their solutions, and also there were mathematicians populating the zulip who could weigh in. So basically, we had this process by which the community could weigh in on whether a given solution was correct or not. But yeah, so anyway, so having done this, we learned a lot of information about, and it made us think about how we wanted to structure the second batch as a more formal benchmark, where transparency was really a key thing that we wanted to highlight.
Great. Well, before we move on to the second batch and how you're implementing what you learned, Rachel, you said that at Microsoft, I think it was, you were working with small language models as opposed to large language models. Did any of the small language models attack this first batch of problems, and how did that go, if so?
Oh, no.
No.
Presently there's quite a difference in capabilities in doing parts of research math level proofs between small language, by small, maybe like 1 to 10 to 50 billion parameters, versus frontier level systems. The small language models are presently most effective at doing more specific maybe not rote, but just formulaic tasks, in which they can be just as good as frontier ones and could be used because they're less expensive.
So just to understand the difference, you said, is the difference measured in parameters, as you said?
Yes. When I say small versus large, it's just the number of parameters in the model.
What are the numbers, or what is the ratio?
So
how many orders of magnitude?
I haven't been keeping up with the current cutoffs, but at the time, small language model meant maybe like under 10 or 20 billion parameters in the model. And large language model, which sort of refers to frontier level model, closer to 1 trillion parameters, on the order of 1 trillion.
Okay. And is the process, though, the same besides the scale in terms of pre-training and reinforcement learning, or we don't know really how the frontier labs are trained?
I would say that the process could be similar, but it's a lot more direct for smaller language models. For smaller language models, there's sort of I believe still a certain formula for the sort of type of architecture, the shape of the weights, the number of layers, and so on. And the good set of parameters to use in the stochastic gradient descent optimization method, and a good number of, size of training data ratio compared to a number of parameters and so on. And I want to say one thing, which is that these frontier systems, at least the publicly available ones, these pro systems, they're not just models. They're not just an architecture and a set of weights, but there's a lot of inference inference level compute going on, and interaction, and different model roles like verifier, author, code generator. So it's more of a system that operates for a good amount of time before producing the final answer output tokens.
I see. And there's a question from Pavel Eddinghoff. Are small language models, are there some of them that are being trained in specialized math areas? Are there some that are being trained more generally in math, or are they not doing math?
As far as I'm aware, small language models are not expressive. They're not strong enough. When you have 1 billion to 10 billion parameters only in your AI model, it's just not large, expressive, powerful enough to get to be competitive at producing proofs, mathematical proofs that are reliable at the level of graduate level or above.
But Rachel, I think part of Pavel's question is, has anybody actually tried this? Has anybody tried to build a model that would be like, I will take, finite free probability, whatever, and I will train a model that will know everything just about that?
Okay. I think that makes sense, that one might try that, but I imagine that if one actually tried that, they would realize that math is more interconnected. And it's not just that we have these independent, separate branches of math, but in order to get very good at that sort of very specialized, specific type of math, you have to be good at all of math.
So I think if we look at the solution to the Erdos problem from a week or two ago, the unit distance conjecture in the plane, that would be an illustration of just what you said, where the problem is about these configurations in the plane, but the solution was about towers of number fields with certain growth properties, right?
Yes. It's very likely that if you want to build something like that, then you need a much broader background that you're putting into your model. I do want to say one thing is that there is some discussion among the AI startups of trying to build some dedicated to math large, medium, I don't know, language model, but nothing has been released. It's just people saying that they want to do it and they have the money to do it, but we'll see if it ever happens.
Okay, well, there are lots of interesting questions in the Q&A, but I'm looking at the clock and we may come back to them. But Mohammed, why don't we go on and get back to first proof in particular and pick up where Lauren left off about what lessons did you learn from the first batch and how are you implementing them and structuring the second batch?
I think the fundamental lesson we learned is how hard it is to check the correctness of AI proofs. Sometimes you have an expert look at it and just say like, well, there's an error in the first paragraph. And sometimes, like actually happened with the problem that I submitted, you have a 13-page long document, and the strategy looks correct, but to get a human to sit down and check it will take multiple hours of their time. And even if one human were to check it, I would not be confident that that there was no mistake unless there was like at least a second set of eyeballs.
You
So
should point out that your own solution was 3 pages.
my own solution was 3 pages long. Indeed. But that's another story. Yes. So the kind of the fundamental that's one aspect. One aspect of what we're changing about this is that we are gathering a group of humans, experts in the areas of each of the 10 problems that have been submitted this time, that we've selected this time. And they will come together, read these solutions, essentially annotate them for where they find any mistakes, where they find any flaws, and then judge them according to some criteria that we've tried to make very similar to the kind of criteria we have for journal submissions. I say that's the aspect, that's the kind of grading part. The other part, which was referred to earlier, was also this problem of not knowing how we arrived at these solutions. In an ideal world, what we would say is like we would like to know how the models were trained, what went into the models, how they were built. That's not realistic. What is realistic is to say, given the publicly available models, how do we go from that to an answer? Okay, the one version of it is, you go and you log on to GPT, OpenAI's website, and you put in your question to one of their models. And if you did that with math questions, you'd realize very quickly, like if you ask a sophisticated math question at the graduate level to the free tier, you will basically usually not get the right answer. If you pay a little bit more for something that does thinking, then you'll start getting closer and closer to a meaningful answer. But if you really want a research level question, you're going to kind of pay this kind of $200 a month subscription or whatever and get something much more elaborate. And as Rachel was alluding to, this more elaborate thing is not the answer of a large language model. Okay, so she said there was a lot of inference time compute, which roughly speaking means that OpenAI sets up some kind of architecture with multiple copies of its models talking to each other and transferring information between them. As she said, one of them is going to act as the author, and the other one's going to act as a critic, and a third one, like Nikhil said, maybe is going to be writing some Python code. So that's at least that's kind of what it means when we're saying we're testing a system. So one thing we're doing this time is we're going to test one of these systems. We're going to test 5.5 Pro because it seems likely that that's the one that's most capable. But the thing we're most interested in is the fact that there are other systems that can be built, and we would like to, I think mathematicians should try to understand how these systems are built and what they do. So there are 3 academic groups that are, let's say combined CS and math groups that have built systems of this type that are able to, or that they hope are able to, answer our questions. And we basically have the whole thing. We will release the code for how they produce it. We will release the logs for what happened when we fed our questions, and we'll release their answers, and we will release our reviews. So everything will hopefully be very, very public, and people can kind of have a clear assessment of how well do the things do. And also we will release how much it costs in tokens. And so that this is less of a black box.
Okay, great. So just so I understand the process, so the first part of the second batch was getting 10 questions. Just roughly, maybe Nikhil, how did that process go? How did you generate the questions for the second batch? And were they different in any way, criteria, than the first 10 questions?
I mean, they were roughly the same type. They should be naturally arising questions with proofs that are not too long. This time we made the limit 8 pages instead of 5 pages. And we tried to cover, have some breadth across areas of math. So they shouldn't be concentrated in one area. And ideally, yeah, we ask for questions that require some insight. They shouldn't just follow, it shouldn't be very close to things that are published.
And again, questions where people had solutions already.
Yeah, the people just were already doing research and had these things, but had not published or discussed them. And yeah, we again relied on our social networks, on just what we know about different fields of math, and gathered these questions from the community.
And so in this round, who is interacting with the AI to test the AI? Are you guys doing? Who's
Rachel.
doing that?
Rachel is interacting.
Rachel is doing that. Okay,
Yeah.
Rachel.
Yes. So this time, so we have more control over the process of how the solutions are generated. We asked the teams to just share their code with us, and we will run the code with a 24-hour time limit on Amazon Web Services. So, I'm basically using, we gave them specifications and what is allowed, like API calls and web search. And then, so I got the code and I ran their code for 24 hours and got the output.
And that's where the process is right now. You have the output, but it hasn't been graded.
Yes, we have the output and it hasn't been graded.
So CMSA, I think, is hosting over the next 2 days what's very familiar from first year calculus, a grading party. And that's the next step. I guess they'll be graded and you editors will look at that. And next Wednesday at this very same time, we're going to have another session with the 4 of you where you'll announce the results. That's correct. Does the public also get a chance to try different AI systems? Yeah. So how does that work?
Yeah. So it's so one thing that people seem to really enjoy from our first batch was the fact that we made these problems publicly available and we didn't release the solutions for a week. And so anybody could try their favorite LLM and have a go at the problems. Now, what Rachel has just done in terms of testing the problems is much better from the point of view of transparency and making sure that we know what is going into the solutions, but has the disadvantage that the community cannot work on these problems because we're going to release the solutions, the problems, the solutions, the results all at once. So separately, we're going to have a community round starting mid or late June, where we will release 2 problems at a time, separated by a few weeks. And here, this is not going to be a benchmark. It's just problems where we will release to the public for anyone to try, and then we will release the solutions about a week later. And so this is definitely not going to be a benchmark. We're not planning to grade these. There will again be an opportunity to get community feedback on the solutions, but this is really so that the community, any sort of math enthusiast or professional mathematician or anyone can just play with these problems and see how it goes.
Okay. Is AI used at all in the grading of solutions?
No, I mean, formally it is not. We're actually might be having an experiment where we try to see a comparison between what an AI grading system might do, but as compared to what the humans do. But basically, the humans are going to just read the solutions and grade them the way they would normally grade a referee report.
Okay. So we'll wait for next week to see the results of that. Maybe in the last few minutes, I don't know if any of you wants to share your future plans or how things are evolving in first proof. I take it second batch is not second of 2.
That's right. So we plan to have more batches. Hopefully, we plan to have about 1 a quarter. I think the main thing I want to say while we have, a captive audience is that if there's any mathematicians in the audience who feel like they have problems of the type that Nikhil presented that could make a good candidate for our future batches, feel free to contact one of us and, we'll see what works. But our next batch is likely to be assembled over the summer and released in the fall, in the mid-fall. And then we will continue doing it again next winter and next spring. So, at some point, it's not clear how far we will go. I mean, AI technology is changing. And another way to say this is that we really have focused on a very clean part of a mathematician's work. Like Nikhil said, it's very easy to check, like, was this answer right? Was this answer wrong? But answering like, did it answer the mystery? What it is that we're doing as mathematicians is somehow that question is a very big question. And, we hope the First Proof and other entities will be thinking more broadly about how AI interacts with math, not just like, can AI prove very well specified statements that we provide it? So I think that's the big question for the next few years.
To just elaborate on that a little bit, some of the things that mathematicians do is to come up with, new conjectures and new ideas and come up with new frameworks for developing solutions. And so, so we really want to emphasize that proving a specified statement is only a small part of the work of a research mathematician. But it happens to be the easiest part to benchmark.
Have you seen, not just in your project, but generally any place where AI has gone beyond that easy part of what a mathematician does?
I mean, I've had informal conversations with colleagues where they've tried to use it to generate good questions. And it seems that the success rate is low. Like someone was saying that, they used it to generate 100 questions over a few months, and one of them was really good. So, that's something.
That sounds good. Someone asked, I think, how they, okay, the questions are coming too fast for me to read them. So I think we'll have to defer answering those questions. I think we're at time. So again, I want to say that next week at the very same time, there will be a link put in the chat now. You can sign up for another webinar where the 4 editors will spend the time talking about the solutions, maybe present one of the problems again so we get a feel for the mathematics involved, and then talk about the results and what happened. I want to also say at CMSA, we have other activities that involve AI and mathematics. Mike Douglas has been running for several years now a seminar about new technologies in mathematics. And we're starting a new seminar in the fall called AI for the Professional Mathematician, where we'll have professional mathematicians, research mathematicians, talking about different ways in which they've used AI. So I think a link to sign up to get information about that is also in the chat. So let me thank the 4 of you, and look forward to having you at CMSA in the next few days for the grading party, and look forward to seeing you next week. Thank you.